I'm going to continue on the topic of sign problem, but this time in using a method different from density of states. We together with Philippe de Forcrin, so we've been trying to understand how to solve, not solve, but to tame the sign problem in QCD. They use the QED as the toy model. And so we've heard in previous talks about the sign problem, and this appears at usually at finite density. So Diageo already introduced what the sign problem is, so I won't take much too long in it. But in QCD, it shows up as when you integrate out the fermion fields, which you need to do in order to do numerical simulations. And the Boltzmann factor that you get in the partition functions is the determinant of the Dirac operator. And at finite density, this is complex valued for all values of mu, except for imaginary mu. But the probabilistic interpretation is lost, and then you need to use some clever techniques to try to extract some information. But the most important thing to understand is that this sign problem is basis dependent. So it does depend on the basis of states in which you trace your partition sum. And so you can imagine that if you were infinitely clever and you could solve your Hamiltonian for QCD and you knew the eigenbases of your Hamiltonian, then you'd not have a sign problem. So this gives you a reason why you could look for a different basis for your partition sum, and so the technical goal of this talk and of our project is to find some suitable basis for lattice QCD or similar theories in which the sign problem becomes sufficiently modeled so we can do numerical simulations efficiently. So for QCD, you think that the sensible candidates for this trace over which you trace your theory, they should be the color neutral fermionic states, just like you have more due to confinement you get in QCD. And so this is why we in this technique of dual variables, you integrate out the gauge fields before you integrate out the fermion fields. So in the traditional way, you integrate out the fermions because you cannot put them on a computer, and then you generate configurations which depend on your gauge field, and these fluctuations can be argued as being the ones that drive the fluctuations that you cannot control at finite mean. But if you integrate out the gauge fields first, then before you integrate the fermions, then you might argue that you get rid of these fluctuations and you might be able to control the system at finite density. But this is hard to perform analytically. So I'm talking about analytical integration. But at bit equals 0, the plaquette term in your in lattice QCD drops, and the analytical integration is very simple to perform. So you get just a linear function of the link variables here, and you can perform the integral over U first, and you get just a sequence of polar singlets on this side by side, and then integrate over the fermions, and you get a partition function, which is just a combination of a combination of monomers and dimers that give you some typical configuration of this kind. So in SUN, you get dimers representing meson hoppings and Carlton. Here you have psi bar psi representing monomers, and then you have the propagation of baryon lines, which are fermions in SU3. And omega here represents just the winding. Omega counts the winding of these loops around the temporal direction. So these monomers and dimers and loops, they are arranged in such a way that you can only have 3 quarks at each side. They saturate the side, so it's a constrained system. And for these constrained systems, the worm algorithms that Philippe mentioned, they're very efficient to just modify. They're very efficient to generate configurations like this, and even in the current limit, it becomes very efficient. But for in SUN, even at p equals 0, you have a sign problem because the shape of these the shape of these baryon lines, they introduce some factor sigma here, which can be plus or minus 1 depending on the geometry of the loop, and this has to be reweighted over. You can reweight with respect to this sign, but what we get is a very mild sign problem in comparison with the traditional approach of integrating the fermions first. And if you measure with this delta F, you get an improvement of a factor of 10 to the 4, which means that getting the same sign problem in this approach, I mean, in the traditional approach, you have the sign problem with 10 to the 4 smaller volume. I mean, you can go to volumes 10 to the 4 larger before you hit the same sign problem. So it's a very useful representation of the partition function, just using these monomer and dimer variables. And you can go beyond b equals 0, the strong coupling limit. But in that case, you have to expand your plaquette term to the order you want, and then you perform the integral over the link variables first. And this can become quickly very hard to perform. I mean, but so at order beta, this has been studied by Cochran and Unger, Langland, Tillerson, and so you just get some plaquette occupation number as an additional degree of freedom, and so an expansion in powers of beta, and additional constraints for your system. But again, you can simulate this system very efficiently with a worm algorithm. And the sign problem is still mild enough to allow numerical simulations, and in particular, you can actually map the phase diagram of lattice QCD at this order beta very efficiently. Of course, if you want to go beyond powers of 2 beta squared, beta cubed, and so on, then this becomes increasingly hard, and so probably a new approach is required. And this is what we've been searching for. So we want to integrate out these link variables in your partition function exactly for any values of beta and without approximation. But there must be a trade-off. And so this trade-off is to introduce some complex variables or complex matrices in the case of SUN. And you introduce some extra variables and you integrate out U. We do this just by doing some Hubbard-Satonovich transformations that split this product of 4 variables into 2. So here you have a representation of the plaquette, and then if you introduce these Q variables, you split it in a product of 2 link variables, and then if you do another Hubbard-Satonovich transformation of these terms, you get a linear term in U, which you can then integrate out analytically. So the integrals that you get after all the Hubbard-Satonovich transformations is one link integrals which are known to be, some solutions are known for these integrals. And you have some source term here, some factor here that depends only on the auxiliary variables. So you get rid of the fluctuations of the gauge fields. And so the Wilson loops will also be given in terms of these quantities via some effective link. We apply this to U1 lattice gauge theory, and because this is the simplest case before going to SU2 or SU3, and we in this case we need to introduce complex numbers on each concat to decouple the four links in the U1 Wilson action. And these integrals are very easy to solve. They just involve modified Bessel functions of this quantity j that I showed here, so the absolute value of this j, and in the end you get a partition function which is exactly equivalent. This is the pure gauge theory, which is exactly equivalent to this case, but with extra variables, just got rid out of the link variables. And so the Wilson loops are represented in the same way, but now just in terms of these Q's and R's, and they have also a very simple expression. So we only use this as a toy model to, and so the generalization to QED is very straightforward. So you pick up the pure gauge theory, and then you just add some fermions. In this case, they are staggered fermions, and you can, and since and after integrating out you can then perform the integration over the fermions and get again the same combinatorial objects that we get that represent polar singlets, so monomers and dimers, and also now electron loops. And these electron loops, they carry a negative weight, just like in the case for SUN. But in addition to that, we also have this extra factor that comes from computing these at finite theta. This is just the value of the Wilson loop following the electron lines, and this can also be negative. So this is the trade-off that we get from trying to integrate out everything at arbitrary values of theta. So there's also, it's also easy to get from here that only the zero binding contributes as usual, but this does not help much in the sign problem. But we still hope that this sign problem can be mild, or milder than if you just did it in the traditional way. And so and our Monte Carlo algorithm so we try to simulate this system with this following algorithm. So we integrate out over the auxiliary variables. These are bosonic variables. These just the Gaussian path. We perform the Kubat-Satonovich transformations with the help of some auxiliary U1 field, which does not appear in the partition function, and then some metropolis to correct for these Wilson loops that go around the electron loops. And for the monomers and dimers, you just do a typical mesonic worm algorithm, which just updates the monomers and dimers. This has been done before. And for the electron, and then for the electron loops, we update them with a worm algorithm, which has a specific weight depending on beta, and also a local weight depending on the phase of these Wilson loops. And this has to be reweighted with respect to the sign, because this quantity can also be negative. So these are the two sign problems that we get. So there is a fermionic fermionic sign that comes from the shapes of the electron loops, and then there is this additional sign that comes from the sign of, from the value of the Wilson loops around the electron loops, and we can in our simulations of the Schwinger model on a lattice massive Schwinger model, we can just scan the phase diagram of mass versus size. This is given in units of the correlation length, and if you just increase the lattice size, you see that there is this additional bosonic sign problem gets even worse than the fermionic sign problem. So this is the trade-off that I was talking about. We were able to integrate out over the gauge degrees of freedom exactly for all values of beta, but we had to replace them by something which also fluctuates, some other bosonic degrees of freedom that fluctuate, and make the sign problem as bad as before. And so in this particular case, the sign problem shows up in this corner because you have these Wilson loops, and for small beta, the expectation value are very close to zero, so they have a tail into negative values, and this gives you some negative configurations here. And so the solution to this sign problem would be, again, to try to integrate out these oscillating degrees of freedom, these bosonic degrees of freedom, in order to get some reduction in invariance. So we try to do this, and for our system, let's consider just the pure gauge theory, because in the general case this works exactly the same. So we just factorize the radial and polar part of our auxiliary variables, which are just complex numbers in the U1 case. And so now you have this J quantity here as a function of the radial part and the polar part. And you start by absorbing the link variable, the link variable itself into this phase of these R's. And so you get some term which depends on this, basically just the wedge of a plaquette. And doing so, now we integrate over the phases of the Q variables, and then we get an expression which, together with the expansion of these exponentials in terms of Bessel functions, you get something. Which is familiar from expansions in U1. And after integrating out over the variable, the phases of the Q variables, you get a combination which is just the phase of a plaquette here, but you still have two phases left. So integrating over the phases of the link variables, then you get you get a constraint on these additional numbers that show up. So these indices that label the modified Bessel functions, they become plaquette occupation numbers that are our new degrees of freedom. And these are constrained by the integration over the plaquette. This just means that the sum over a bouquet of plaquettes around the link must vanish at every link. And then finally, integrating out over the Q's of the phases of the R's, you get just another Bessel function. This is just the integrand of a modified Bessel function, and so finally you get an expression which is free of the sign problem. So if you introduce this on the partition sum of Lattice QED, then you get this fermionic sign that comes from the shapes of the loops, and then a purely positive definite weight for for the bosonic sector of the theory. And so, and in this case, if you after introducing these fermion loops, you get a modified. So you get a modified constraint, which says that the sum of occupation numbers on a bouquet around the link should actually coincide with the fermion content on that link. So our Monte Carlo algorithm that we're working on at the moment will be a little bit more complicated than in the previous case, but since there is no sign problem, we only expect to see. We only have to reweight with respect to the fermionic sign, but this we cannot expect to solve at the moment. And this just involves a sequence of IPBAT and Metropolis for the bosonic part, and also worm algorithms for the monomer dimers, and possibly for the electron worms. In 2 dimensions, you can just do the usual electron worm, but probably surface worms in higher dimensions. And so we know from previous work that you can successfully integrate out analytically the gauge degrees of freedom at some order in the strong coupling expansion of Lattice QED, and this gives you very good results in mapping the phase diagram, understanding the phase diagram. But in order to go beyond beta, we want to integrate for arbitrary values that can get us closer to continuum limit, and we try to do this in QED just by integrating out, by replacing the gauge degrees of freedom with some absolute variables, and but the fluctuations of these absolute variables introduce an additional sign problem that we have to get rid of, which we did by integrating over their phases. And so in the future, we want to check how the fermionic sign, which you cannot get rid of in this model, behaves with this new partition function, and eventually go to larger gauge groups and try to apply the same method. Thank you.
I have time for a question, maybe? Okay, everybody wants coffee, so let's thank the speaker again.
So there's a short announcement, please.